Two comments. First, Marco already said 3:30 to 4, and then we just figured out how to make it so there'd be a stagger. So Emmanuel will be available 4 to 5, and I'll be available 4:15 to 5:30, some combination of Claudius or I. And that way, if you have questions for everybody, you can just schedule your time and make sure you come and find us. And then the last thing I wanted to say, I know Gregor made sure we took this, but usually cultural differences everywhere. Make sure I said thank you to the organizers as the last speaker of this week or the last 2 weeks. It was really fantastic. It's an unbelievable amount of work, and I really should thank them more than once. So let's go. Okay, great. So what I want to do a little what Marco did and try to step back and chart out some of the bigger picture, continue to try and make some connections with other lectures that we've seen over the 2 weeks, and maybe state without proofs. So I just want to recall where we were at. So last time, we saw KH, this funny new notation. So this was a particular representative of either a chain complex or a type D structure or a twisted chain complex, there's at least 3 different ways of seeing this. So let me say complex type D structure over R. How do I want to think about this? So this really is just it's the polynomial ring in one variable over coefficients in some field K. And we could think of this as an algebra with a single idempotent and a single algebra operation, or equivalently, a category with a single object and one morphism, one interesting morphism called H that I can compose as many times as I want. Okay, so view in terms of however you prefer thinking about these at this point. So view as a category or an algebra. Okay, so what does that give us, this particular representative? So the surprising fact is that this admits, so the main point here is this admits a graphical representation. And so just to up, but I cooked up a slightly different example. So here's the first thick knot, the first knot whose Khovanov homology has more information than the underlying Jones polynomial. This is my knot for this example. It turns out that this is also known as 819 in Rolfson's tables, or the 3-4 torus knot. Okay, so I'll tell you the answer here. So there's one, we're expecting one free summand that corresponds to some idempotent, no arrows out, and the rest of the type D structure looks like this. And this is just an alternate representation for something we've seen in various guises at this point. So what is this? This is This is this particular representative, KH, so this K we talked about last time. Again, so you can interpret this in various ways. And you can extract the Barnaton chain complex from it. Okay, so representation. Decorate things suggestively. So here's a certain annulus, so S1 times I. And the way to read the algebra off this picture is that you've got this green arc sitting in the boundary. That just is, that's assigned to my, I'll just make one of these so it's not confusing. The green arc is assigned to my unique idempotent, and then there's a single operation that goes from the green arc along the boundary, green arc, and that arc is called H. And this gives us the recipe, taking this fully canceled and cleaned up representative and just presenting it as a collection of colors. So it should have 1, 2, 3, 4, 5 generators. And then the component with no differential just runs off the inner, and there's further something that spirals around the inside twice. That gives me a H squared operation. And then finally I have curve here. So if I want to make generator called B, here is that generator called A, and here is generator called B. And in the differential, B of A is B with a copy of H that it picks up. We run along the arrow, and that's this arrow here. And I'm claiming you can drop the orientation on the edges because we're using the orientation on the boundary to tell us that there's a differential going from A to B and not the other direction. Right? You go from B to A, I'd see an extra fishtail in there. I picked it at funny heights here so that this is not exactly unique, right? I could move the points along on the boundary, and I might add or undo some self-intersections of this system of arcs. But at the end of the day, all I'm doing is this information and placing it in the annulus. And that's not, that's just a fact about simple graphs. I'm able to do that. They're randomly, and that's why it's not unique. The position of the dots on the boundary, I just picked them at random. So that's what I'm saying. If you change the order, you might put extra self-intersections in between the arcs. In particular, there's an intersection I didn't need here. I could reverse this order, and that's an ambiguity. But this is sort of not offering this with any warranty at this point. It's just a suggestive picture of where we might go if we're trying to think about classifying these modules. So now what I want to do is tell you the theorem in general. So here, all of the linear algebra happened using the cancellation lemma and the cleanup lemma. So we had this really simple picture. I don't really gain very much by putting it inside this annulus, except that it does a little bit of foreshadowing about what's coming next. Okay, so in particular, when working over this algebra that we get from thinking about Barnaton's category, so this is the algebra that has two idempotents and these saddle morphisms and dot morphisms. And like 0, which is the thing that makes many of the chain complexes satisfy d squared 0. So now things are a bit more complicated. So this is not just a question of cleaning up and canceling anymore. So this is a theorem. This is a theorem that's sort of driving these lectures all the way along. So how do I want to say it? So the type D structure. So given the type D dt, which is now something that makes sense for B, admits a representative an immersed multi-curve in the boundary of the tangle, so in S2 minus 4 points. Okay, so components can take one of two forms. So either these are non-compact, they're non-compact, you can say a little more. They have their ends are on the non or I guess I've punctured this, right? So the non-star punctures. Crucially here, the whole story, let's remember that one of these points is distinguished with our choice of mark, the star. Okay, so one point is a priori special. The other thing is I have compact components. And here's where things become a little bit more interesting. These may carry local systems. What does that mean in practice? So this is i.e. some k vector space plus an endomorphism of that vector space. Okay, so that's the playing field, and you should compare this with what we learned last week during Anna's talks, right? Okay, where she went through a proof of something for algebras of this sort coming at it from a different point of view. Okay, so what is this? What's going on here? I should. The important part is this representative up to homology. So that means up to it's immersed in the the sphere minus these 4 points. So we give the Barnett invariant of the tangle T. So through this long process all week, we start with Barnetton's double square bracket of T. Having marked an endpoint, one of the 4 endpoints of the tangle, we can massage that to see it as a chain complex over a much simpler category, or reinterpret it as a twisted complex or a type D structure. And then, working harder with those particular derivatives, you can show that they admit something much simpler, that in fact you can forget the underlying chain complex structure and just preserve an immersed curve that's sitting in the boundary. Okay, so we've gone from geometric information, some passage through complicated algebraic manipulations, and returned back to a geometric object. Okay, so over. This is compatible . So I should say, I won't write it down, that the approach to simplifying our representatives is done in close conversation with the morphism spaces, so that we know how to perform reassembly at the end and compare that with Barnetton's reassembly. So by checking that it's compatible with reassembly, following is true. So if I would like to recover the Barnetton invariant, let's remember what my convention was for gluing things together. So I had used to be orange, so let's keep it orange. It's blue, unfortunately, but I'm realizing that's actually a different orange than before. So for people judiciously looking for a color code that was consistent, but here we go. That's a knot, and what we're showing now. Notice I've just put in the homology here. So I'd like to take the homology of a space, the intersection Floer homology between curves, and those will be, you write it this way. Well, I'll put the mirror operator on the outside, so I still have this perhaps annoying mirror on the outside to one of the objects. Surprising, to represent these objects, I have to choose an inside and an outside of the sphere, and one thing has to be mapped onto the other sphere to make sense of this intersection. Okay, so this intersection is all happening, say, T's boundary, maybe T primes. Okay, so this means that in practice, if you quickly want to know the total dimension here, you're usually just counting a minimal intersection number between 2 curves. This can be powerful. That's one of the things that I want to make sure I say is what this is actually, something this tells you. So it's valuable to have an example. And so for the example, what I'll do is I'll cut a tangle out of this picture above. And in hope that I make it there, I'm going to cut all but one of the crossings out and say a little more about the construction in a moment. So there's a subtangle of that knot K, and we could wonder, well, what is the answer? What is the Barnetton curve associated with that? Well, here goes. What I'm going to do is I'm going to puncture the back face of that sphere and send that out to infinity so that we're really just staring at the front face. And that somewhere on the blackboard, I'm going to see my endpoints. Okay, so now I'm going to like draw out the type D structure from it. It's clearly not the direction the theorem goes, but let me use green arcs here to divide this. Now it's a 3 punctured disk, if you like. I want to divide it into 3 annuli along. And just like I had before, I had a recipe here that said where the idempotents went and how to walk around and read off algebra elements. So there'll be an idempotent here. One of the 2 arcs is assigned to an idempotent, and the other arc is assigned to the other idempotent. And then the recipe, so the key for the map, is how do you walk around between these arcs? So as you do a tour, an oriented tour of that starred point, what elements do you read off? And these are S, D, and S. Okay, so this is some foreshadowing to what's going to happen. It's just feel like it's coming out of, 1, like it's coming out of nowhere, but 2, based on the color coding, like it's very similar to the recipe I cooked up here. So now what I'll do is in blue, I'm going to draw the Barnaton curve associated with this tangle, but that's the tangle right there. So here's the curve. Okay, what on earth does that mean? Yep. The two mixed chords are both labeled S. I don't understand what you're asking yet.
There are 2 chords labeled S.
Yeah.
They both go from the 2 stated chords.
Yeah.
But they are different.
No, they are different. Remember, these can't communicate. There's a puncture at infinity at the back of the sphere that they can't move past. So those are different. Those are different chords.
Yeah.
Oh, yeah. I've been labeling them with the same. I have been uncareful on that point. So this is reference exactly. Still just, out of nowhere. So what I want to do is to as a rationale, I want to now draw this. How should we read it? This is a single non-compact curve as promised by this result. And now I'll read off what this distinguished type D structure is. So here, the intersection points have 2 flavors, right? As you pass around this curve, intersections. 1, 5, 6, 7 second points. I have total dimension of my type D structure is 7, and it's split into something of dimension 4 and something of dimension 3 according to the idempotence. And now, starting here, say, I won't label all of them, but I do have an A and then a B following along the direction of this S map. So what I'm expecting to see in the type D structure is a map that takes in an A and it produces a B at the expense of adding an S on the right-hand side. So that's what part of the type D structure looks like. Okay, so that's that part of the type D structure with an S on it. And then now let's continue reading around the curve. So there's a dot, 2 dot, that's one of my D's, following the orientation of that D. And then there's another, well, it's not an S. It comes back from dot to dot. So it's actually following an S and then another S. So that's an appearance of an S squared thing. It's my S squared. Then another dot right here. And then finally an S. That's this S here. And this is a D running the other direction. Okay, so let me just use different colors to single out a couple of, just as a roadmap for people that may have been fast. So here's this purple D. Where is that? That's this part of the curve. And it runs that way because of orientation on the D. Okay. Maybe one more element of the roadmap. This S squared is its things that we've seen. Here. And it's following around in the right direction, but picking up two S's on its way around. This S squared. Okay. And just because we already labeled them, A and B are here. And I didn't give names to any of the other generators, and there's a question. Yep. No, this is a tangle. It's tangle. I'm taking all but one crossing of that tangle. So I removed the crossing. But I memorized it. So I memorized it for the purposes of the talk. I memorized it to give an curve, and I'm reverse engineering. Is proved. Right? So the way the theorem is proved, you start with Bonneton's object. You start reducing it to in this pair of dots, which will lead you on something like this. And then you go this direction and realize that as a sub-gadget in here. I'm going back to give a specific example. The first thing is I want to tell you what a consequence is. Then the next thing I want to try and do is tell you, what happens in general and why, for example, but you just a curve at the outset is not what you should expect. And then if there's time, say a little bit more about the structure of these objects. Okay, so this in consequence, notice that this tells you so what you learn from the theorem which isn't obvious about these types of structures at the outset, is that it is possible to find a representative of the type D structure itself and that this, I'm going to give this a particular name. This is exactly, once you've found the curve, you can go back and you can write out the type D structure that corresponds to that curve. So this is going like, you start with an arbitrary type D structure. It might be a complete mess. Then you slash theorem. That's going to give you an immersed multicurve. That immersed multicurve is giving you a particular representative back here, curve representative. The thing that directly, some direct translation of Bonneton curve using green recipe of the sphere. Okay, so what does this represent? It looks like two pieces, say the compact part, so there's some collection of curves that are non-compact or open. Curves and open curves, or non-compact curves. So there's an a posteriori splitting of your complex into two pieces. Okay, and then it is not obvious, but it's possible to show that if you a knot, okay, that's represented as a pair of tangles. We have this particular free summand that we know there's exactly one of in the Barnaton homology is listed from just the T in the non-compact and then the other type D structure. So it's the non-compact curves to non-compact curve intersection that are going to contain this tower. Right, so this is the whole story, right? This is some sub homology. So I should have let me do that. So homology here. This is inside the Barnaton complex of your knot K. Okay, so now we're going to look at these two statements. The non-compact components have nothing extra complicating them. It's the compact components that have local systems on them. The local systems, they're a feature and a bug, but for the moment, they're not of our concerns. We're just intersecting pieces that don't have compact components. What you learn is that the S invariant, and this is now not going to depend on of its mutant, are going to have to agree. So this is Rasmussen's S. S invariant over K. So proof here. Well, the morphism of the input type D structures this is something that if we look through the last couple of years, so if I ignore signs, I can replace T by its mutant. And another way to ignore signs is to put the intersection between the non-compact components everywhere. And these are going to agree. So what's happening is that the S invariant here, which is the grading on this free summand on due to time, didn't tell you more about grading, but that's how, based on what we have, that's what we learn. Okay, it's our first clue that can say a little bit more that we can do with at this point. You at least deal with signs on the non-compact components. Okay, so that's a first desired point of arrival. Yes. Yeah, so that's exactly the next thing I was going to say. So thank you for the question, Paolo. Excellent. The key point compact components. So can one-dimensional local systems for instance, maybe they carry that are just the endomorphism multiplication 1 as you pass around the curve. And these local systems ultimately control signs. So in fact, they're the one thing we don't have a handle on in taking a general statement about the Barnaton invariant being invariant up to mutation and moving that from a mod 2 statement to a free statement about any field. Yes, Gregor?
When I try to put together the theorem down there,
Uh-huh.
so there, I'm saying that there's at least one non-conforming point, or are you saying there's exactly one?
That is an excellent point. No, there's at least one, but there's not exactly one. The exactly one that's happening is because when you start with a not, you know that there's exactly one of these, and it's coming from. So there's a few different steps in there. Yeah. So there's at least one. Yeah, that's good. Question. Mm-hmm. Well, it comes from the geometry of that 4 punctured surface. So it's somehow bestowed on us. I guess that's really what it comes from. You realize, these are exactly the types of algebras that are being studied in this HKK setting, for instance. There's other hints, though, of course. There was a predecessor to this that came from Both Heegaard Floer, where the boundary torus was in place. So you'd really like the boundary to be the right place to send this invariant to. There's really only one way to make a link between that surface and the algebra that you're given. And the algebra you're stuck with, that really is Barnaton saying this is the algebra governing the Khovanov invariants of tangles. OK, so to spend 10 minutes on one thing and 10 minutes on one thing. So, yes? Yeah, and so I want to start to gesture towards how you might do that. I'm not going to prove that today, but this can be handled. But it is telling you what you need to do. You need to stay. Now we've spent most of the week understanding as best we can the morphism spaces. Now we have to go back and try and get a better handle on the objects. This is the first pass. The objects are all different types of immersed curves. Now, if we can get better control on which compact objects come up, maybe we can learn something about and which local systems come up. That would be the program. And I'll tell you, I won't tell you the sign story, but I'll tell you what kind of control there is, at least mod 2, which gives you a strong hint about what we're doing. OK? Yep.
So decomposition of curve,
Mm-hmm.
If you start with a type B structure,
Mm-hmm.
is it true that it always decomposes as you have some of complexes stacked down and some close to complexes?
Complexes like what?
Like the one you showed.
This one here?
Complex.
Yeah. The non-compacts, if you want to say this just in terms of 2-valent graphs, they're either going to, the graphs are either going to be 2-valent but with ends, with distinguished single-valent vertices, or the second type is they're almost loops. But actually, there might be a series of loops running side by side, and then some section of that graph where there's a whole bunch of information passing between the loops. And that's what gets packaged into this local system. So it's not quite just two flavors of curves. The compact curves carry extra data. This is the form of a vector bundle. Yep. You're worried about the fact that that special puncture is not involved?
No, it's not so much a special puncture, but the fact that we don't have anything to circle the curve punch.
Well, I think that we'd have to talk more for me to understand your concern. I guess I don't totally understand. Great, that's good. Okay, so let me try to judge what is at least, so somewhat lengthy example, well, shortened. So these type D structures, again, so we go back exactly to the question, like the kinds of graphs you might see. So here's one. We're imagining this is some part of a type D structure that I'm attempting to understand. Okay, so it has the total dimension, well, this part of it has total dimension 6, and it looks like a graph. And then to know what the del operations are, these all have to be decorated. So here's D, D, S, S, and these are S's. Okay, so there's if there's a secondary way to view this, I could, instead of puncturing the back of the sphere, I could actually puncture at that special point. Especially now that I know that I'm never going to end on that point, I can send that out to infinity. So I could instead, for the algebra, look at it. I want to go back to convention. So this boundary is my special puncture star, 3 additional punctures. Green arcs that's cutting the surface up, and they have 2 different roles with 2 different idempotents, and now running around the boundary is my D, S, and indeed there's 2 different D's and 2 different S's. And similar to this rule that Claire was talking about last week, when you pass directly something 0. So S times D is 0, D times S is 0. Okay, so there's another graphical representation. It's really the same graphical representation, where I sent the star to is different. The star now is off in infinity, if you like. But this one gives us a slight connection to the picture that's sitting right here. So I might, maybe I don't need all of this yet, but this part of the type D structure as a curve, let me put it in blue. There's a pair of idempotents, the open sort, and then there's 4 of these closed idempotents here. Okay, and so what happens? There's part of the curve is an S, and then a D, and then an S. That's the part that's running out around the outside here. Okay, that's me just, again, I'm following the recipe where I'm sending things into this part of the surface so as to record all of the information that's in this graph. These are equivalent information. And this is very much non-unique. Let me just try and make a choice here. So now I've got everything but this edge. Okay, so around this part of the invariant, things look like a compact part and a non-compact part. Everything's going along great, and then there's this one curve that changes between the components. And this is the new wrinkle that's arising. So I can still immerse this. That'll look like this. No, it won't. Apologize. So it's going from this figure 8. That's what's given by this D and SS. Right? And is leaving from the figure 8 and going to the outside non-compact curve. Because we're imagining this part. I'm trying to illustrate exactly where the additional work has to happen in order to turn this into a curve. So this is not unique. But the fact of the matter is that any one of these graphs associated with a type D structure can be immersed in some way into this 3-punctured disk. There may be ends on these punctures, but there won't be ends on the outside puncture. That's what we're expecting to see. So what you can do is this now is related to cleanup and cancellation. And this the faces can be simplified. And so what would that look like? So now I'm going to stretch out the green section. And I'm going to try and take all complicated information and put it into a strip. And then I'll have these remaining parts here. That's where I'm going to put all the messiness and the rest of the train. So what's happening in blue? Okay, so I'm making my green arc longer, and I'm trying to absorb all the complicated matter in there. And I claim it's here. There's two types of complicated things happening. First thing is those should feel like permutation processes, and then there's parts with playing the role of small basis changes. Okay, so let's just check that this has the same information in it. What happened to the purple curve here? The purple curve now leaves from here and runs up the blue, up again, and around. That's that D. Somehow these ones, maybe. Okay, so this is the purple D map by following that particular part of this. Now it's going to look an awful lot like a train track. It's two types of switches. There was a question. Where's S squared? That's this one right here. That's a great question. So this here, that's S squared. Oops, so S squared, SS. Okay. And so it's starting from the and it's running twice an S and then another S. Okay. Thanks for the question. Okay, so I think I'm at risk of making a long story long. The trick is that we to find a way to get rid of pieces like this. These are ultimately, if I'm able to get all the complication contained inside these vertical strips, versions of these cuts, then it's these switches that run between horizontal strands that are keeping me from being an immersed multi-curve. The problem is this is now not a unique representative. Okay, so if you'd like you can write this all in terms of matrices. There's something of dimension 4, and there's a change of basis that corresponds to a permutation matrix composed with change of basis that of the form x goes to z goes to x plus z. Let me now label things just so we can x, y, z, and w in this particular representative here. So that, if I'm being careful, this is x, y, z, w. And I haven't given names to these open idempotents. Okay, so if you like, you can write this in terms of matrices. Notice that I could instead have written this internal green strip as do the permutation second, but at which point switch would have been down here, and now that switch is crossing over and in between. Okay. So if you go, this is my x, y, z, and w to keep track. You can show is, let's try the isomorphism that takes z to z minus x. Okay, so that's a change of basis corresponding to this strip, and I claim that that's having pushed this all the way to the left-hand side. Just change of basis, move it up to isomorphism, and concretely and directly. So I should have left more space. So the rest is going x to x, y is going to y. So this is my new z prime, if you like. And then there's a w, and it's staying at w. So what happens to del now? So del of z prime, that's like taking del of z minus x, which is, what's del of z? So del of z has the part from the purple part. So that's w tensored with d, and then other stuff plus y tensored with and minus x to w with a d. So this is minus x or d. They're going to cancel. So the slogan or the moral, so we learn is to arrive at the edge of this region, and you have a curve as in and a curve that goes out. So this is sitting face. Do this, and I apologize. So this is my face. These are the faces that can simplify. This is a face, and this is also a face, but I'm concentrating in this rightmost face just for this particular example. The faces of this decomposition, and then I'm trying to thicken up these regions with these complicated combinatorial descriptions of basis changes ultimately. And so the claim is that if you see this configuration in the first string, then this is a removable arrow. This is intensity, and that's why it cancels. Thank you, Gregory. Like doors. Thank you. Okay, so simplified type D structure is the same picture you're looking at, so it does not have this arc. That's been moved as possible to the right. Moved. Now there are more than just one removable arrow. There's a few, and you need to decide if there's an algorithm for removing these, because as you slide them around, they could produce additional arrows. It starts to feel a lot like it should be possible to get rid of all of the arrows if you just are patient enough. But showing that that works, well, you're convinced that it will work long before you know a proof. But there's a from that first shows up with Hanselman, Rasmussen, myself. There exists an arrow sliding algorithm and containing curves. And maybe this is enhanced. To work the sign, in this paper that I've been course of the week. And ultimately, you have to have some mechanism for decorating parts of the operations with signs to keep track of, in particular, that sometimes have tape, and you'll collect those. They come along for the ride, but ultimately don't appear. You apply in the setting to prove the theorem that I just erased, and to be honest, it's the first time I've ever tried to describe that such an algorithm might be possible in the first place. So there we